Section: Introduction. In this section, we discuss recent advancements in video-based multimodal large language models, or video LLMs, which have greatly enhanced AI's ability to understand and describe video content. A common method in these models is to treat a video as a series of individual frames, processing each one separately with an image encoder and a visual language projector. The frame-level outputs are then input into a large language model that analyzes the sequence of events in the video. However, this approach has limitations, especially with long videos, as it lacks explicit temporal encoding, which is essential for capturing the timing and relationships between frames. This means the language model has to guess these relationships based only on static images, which can be computationally heavy and hinder its performance with longer videos. To reduce computational demands, existing methods often use simple frame subsampling, which can lead to significant information loss by discarding important frames. Additionally, these methods do not effectively compress consecutive frames that often share similar information. In our work, we introduce STORM, which stands for Spatiotemporal Token Reduction for Multimodal LLMs. This new approach adds a temporal encoder between the image encoder and the language model, allowing for better integration of temporal dynamics early in the process. By embedding temporal information directly into visual tokens, we lessen the burden on the language model, enabling it to concentrate on more complex language tasks. We utilize the Mamba state space model as the foundation of our temporal layer, which allows for efficient processing of long videos and improves generalization to longer timeframes. This temporal layer treats images and videos differently. For images, it enhances tokens by adding global spatial context, while for videos, it captures both spatial and temporal information simultaneously. The Mamba layer's key benefit is its ability to compress past information into state representations, efficiently processing and sharing temporal information across the video sequence. This results in visual tokens that summarize the video's temporal dynamics, allowing us to use fewer tokens for language model processing without losing critical details. In our experiments, we test a straightforward token reduction method that does not require training, which reduces computational costs and improves performance. We also explore training-based compression methods, including temporal and spatial token compression. Temporal pooling cuts down the number of tokens over time, while spatial average pooling reduces tokens per frame. These strategies are optimized during training to keep essential information while minimizing redundancy. Unlike previous methods that simply discard raw video frames, our approach maintains crucial temporal information in a compressed format, reducing the load on the language model and enhancing its performance through a more effective video representation. Our evaluation shows that our proposed method effectively extends to long context video understanding without sacrificing training efficiency. In the next part, we will look at related work in vision language model architecture. Vision language models typically use two main approaches to process visual input. The first approach keeps the language model weights fixed and integrates visual data through cross-attention mechanisms. The second approach uses a pre-trained image encoder, like CLIP or SIG-LIP, to convert images into tokens, which are then combined with text tokens for the language model. This method can be adapted for video understanding by treating videos as sequences of images. To improve video processing, some studies have introduced specialized video encoders. For example, Intern Video uses VideoMay as a video encoder, while Kangaroo employs depthwise 3D convolution for merging video tokens. In our work, we keep SIG-LIP as the vision encoder and focus on enhancing long video understanding by adding a linear complexity temporal module within the Mamba architecture. This module, placed between the SIG-LIP encoder and the language model, effectively boosts spatial temporal modeling. Understanding long videos with vision language models poses significant challenges in terms of accuracy and efficiency. Previous methods have used long context language models trained on short context video data, but these often lack enough long video training data and can be computationally expensive. LongVILA tackles these issues with a multimodal sequence parallelism system that directly processes long video data, but it requires specialized system setups for multi-GPU environments. Another research direction focuses on token reduction to shorten input sequences for efficient long video inference. For instance, Voco Llama and Video XL use recursive cache compression, while LongVU employs features for frame selection to reduce tokens. Despite various strategies, direct pooling along temporal or spatial dimensions often yields satisfactory results, with only marginal improvements from additional methods. In our paper, we apply temporal and spatial pooling for token reduction, achieving better performance when combined with our temporal projector. Section Summary. In this section, we discuss the limitations of current video-based multimodal large language models, video LLMs, in processing long videos due to their reliance on independent frame analysis, which neglects crucial temporal dynamics and leads to significant computational burdens. We introduce Storm, a novel architecture that incorporates a temporal encoder to enhance temporal reasoning and reduce token processing load, ultimately improving video understanding while maintaining efficiency through effective token compression strategies. Section Method. In this section, we present the Mamba-based temporal projector architecture and introduce several techniques for token compression to enhance the processing of long videos. We propose two main approaches for token compression: temporal and spatial compression. We begin by explaining our strategies for temporal and spatial pooling, which effectively reduce the number of tokens during training. Additionally, we introduce a method for sampling temporal tokens at test time that preserves model performance without needing extra training. We start with the basics of state space models, SSMs, which create a linear transformation between an input sequence and an output sequence through a recurrent process. Here, the sequence length is defined, and we have input and output vectors at specific time points, along with a hidden state that summarizes the history. The matrices involved are parameterized with learnable weights to help model long-term dependencies. When these matrices remain constant over time, we can parallelize computations, making training and inference more efficient. Recently, Mamba has improved SSMs by conditioning these matrices on the input, enhancing their sequence modeling capabilities. Mamba uses learnable functions to create input-dependent matrices, allowing the model to adaptively focus on relevant information based on the current input. This approach also includes a hardware-aware parallel algorithm to maintain efficiency during training and inference. Traditional video LLMs often process video frames separately, which is computationally inefficient, especially for long videos. This method does not take advantage of the temporal redundancy in video data, leading to unnecessary processing of similar information across frames. To overcome these issues, we introduce the Mamba-based temporal projector, which effectively integrates temporal information across video frames and enables efficient token compression. We denote the image tokens for each frame processed by a vision transformer, VIT, encoder. We first apply a linear layer to downsample the tokens of each frame to a specified number of tokens. The downsampled tokens from all frames are then combined to form the input tensor for the temporal module. The core of the temporal projector consists of multiple Mamba layers that iteratively incorporate temporal dynamics into the tokens. In each layer, we merge temporal information into the visual tokens using a specific method that includes layer normalization. Each Mamba mixer captures dependencies in both spatial and temporal dimensions through a sweeping scan order across frames. Processing long videos presents two main challenges for LLMs: the high computational cost of handling all frames and the limitations of context length during training. For instance, Llama 3 has a context length that allows for only a limited number of frames when using a specific number of tokens per frame. Without token compression, video processing can quickly exceed the input capacity of LLMs, negatively impacting performance. Our goal is to address both the computational cost and context length limitations by enabling efficient long video processing through token compression in both temporal and spatial dimensions. This approach eliminates the need for specialized system optimizations and allows for inference on a single GPU. To efficiently compress visual information, we propose using temporal average pooling, which combines data from consecutive frames by averaging their enriched visual tokens. Specifically, we average every set of consecutive frames to obtain compressed tokens. This simple yet effective technique significantly reduces the number of tokens processed by the LLM while preserving essential information, making it a valuable method for efficient training in long video understanding. Section Summary. In this section, we present the Mamba-based temporal projector architecture, which incorporates token compression techniques to enhance long video processing efficiency through temporal and spatial pooling strategies. We also introduce a test-time temporal token sampling method that preserves model performance while reducing computational costs and addressing context length limitations. Section: Spatial Pooling. In this section, we explore spatial pooling alongside temporal pooling by applying average pooling in the spatial domain. Given the input from the visual encoder and a specific spatial compression ratio, we use average pooling with a defined kernel size and stride on each frame, resulting in a compressed output. Next, we discuss training free temporal token sampling. After processing through the temporal projector, each visual token gains spatiotemporal information, capturing features from its frame and others throughout the video. This allows us to subsample visual tokens along the temporal dimension during testing, reducing the number of tokens sent to the language model without losing significant information or performance. Our method is advantageous compared to others that might discard important temporal cues by subsampling raw frames, as we utilize the enriched spatiotemporal tokens. We illustrate this temporal token sampling in a figure. Formally, we denote the token input to the subsampling layer, which can come from the visual encoder or compression modules. We apply uniform subsampling along the temporal dimension. Our results show that this method not only maintains performance on various video understanding benchmarks but can also enhance it by minimizing noise from redundant frames. In our experiments, we thoroughly evaluate our method on different video understanding benchmarks, demonstrating how the temporal projector facilitates efficient token reduction while maintaining strong video reasoning capabilities. For training, we use pre-trained models and fine-tune them for our video datasets. The temporal projector starts with random weights, and each image is resized to a specific resolution. In the first stage, called the alignment stage, we freeze the image encoder and the language model, training only the temporal projector with a small dataset of image-text pairs. We find that using just image-text pairs is sufficient for pre-training the temporal projector. In the second stage, the supervised fine-tuning stage, we fine-tune all components using a large and diverse dataset that includes text-only, image text, and video text data, totaling around 12.5 million samples. We use 32 frames for each video input, with specific compression ratios for models that employ training time token compression. Additionally, we conduct a long video fine-tuning stage using longer video inputs from a specific dataset. For evaluation, we assess our STORM model across various configurations on long video understanding benchmarks designed to test video language model capabilities. We compare our approach with a range of video language models, including those specifically designed for long video understanding. We implement STORM based on the Vila codebase, incorporating our novel Mamba module and compression mechanisms. We evaluate STORM variants using different combinations of compression methods, presenting full results in a table. We also include a baseline Vila model trained under the same conditions but without the Mamba module. All models are trained with the same token budget, which is crucial for managing inference latency and memory use as the number of frames increases. We report results for the standard STORM trained on 32 frame inputs and configurations where temporal sampling is applied at test time, which enhances model efficiency and performance on certain benchmarks. Section Summary. In this section, we explore spatial pooling through average pooling and introduce a training-free temporal token sampling method that enriches visual tokens with spatiotemporal information, allowing for effective subsampling without significant performance loss. Our empirical results demonstrate that this approach maintains or even improves performance on video understanding benchmarks while reducing noise from redundant frames. Section: Storm versus existing methods. In this section, we compare our configuration, Storm with temporal pooling and sampling, to existing video LLMs. Our results, detailed in the tables, show that Storm with temporal pooling achieves top performance on all long video understanding benchmarks. Specifically, we reach 71.3% accuracy on MVBench, 72.5% on MLVU, 59.5% on Long Video Bench, and 63.4% on Video MME, surpassing all open-source video LLMs, including those designed for long context inputs like Long VU and Long VLA. We also close the gap with proprietary models, outperforming GPT-4V and GPT-4o on MVBench and MLVU, and GPT-4V on Video MME. Our method is computationally efficient, reducing visual tokens to 25% of their original count before processing. We can further enhance this efficiency by applying test-time temporal sampling, which reduces the token count to 12.5% while still achieving competitive results. This additional compression even improves performance on some benchmarks, leading to the best results on MLVU and Long Video Bench. Next, we conduct controlled comparisons with NVLA-based models to highlight the advantages of our Mamba-based temporal models. We find that by adding the Mamba module, Storm improves performance on 3 out of 4 benchmarks, including a 2.3% gain on Video MME. When we augment Storm with test-time temporal token sampling, we reduce inference time by 43% while maintaining or slightly improving performance, with an additional 0.8% gain on Video MME. This is due to the Mamba module's ability to effectively manage temporal information across video frames, allowing us to discard redundant tokens without losing overall understanding. The temporal pooling variant extends these benefits to long context training, enabling the model to process 128-frame inputs while compressing the token count to match that of a 32-frame setting. This approach not only enhances performance, achieving 63.4% on Video MME, 59.5% on Long Video Bench, 72.5% on MLVU, and 71.3% on MVBench, but also significantly reduces inference latency by 58.4%. By combining this model with test-time temporal token sampling, we further cut inference time by 65.5% and use only 12.5% of the visual tokens compared to VLA, without sacrificing performance. We observe that test-time temporal token sampling particularly benefits MLVU and Long Video Bench more than MVBench and Video MME, likely due to the nature of the tasks. MLVU and Long Video Bench require a global understanding of long videos, and we believe that test-time compression with the Mamba module better captures essential contextual information. In contrast, MVBench and Video MME focus on visual details from specific frames, where our pooling method retains more detailed frame information. We also compare spatial average pooling and temporal average pooling on 32-frame training and 128-frame extension, using Storm as the base model. We find that spatial pooling is effective with 32 frames, outperforming temporal pooling on Long Video Bench and achieving similar results on Video MME. However, with 128-frame inputs, temporal pooling significantly outperforms spatial pooling, which struggles with longer video inputs and shows degraded performance on both benchmarks. Finally, the Mamba-based temporal projector refines visual tokens before compression, preserving key temporal and spatial cues that naive compression strategies might lose. Our results show that Storm consistently improves with longer video inputs during training, achieving substantial gains as we extend from 8 frames to 32 frames and then to 128 frames. In contrast, the baseline VLA model shows smaller improvements and even performance degradation when extending video length from 32 frames to 128 frames. Section Summary. In this section, we compare our Storm plus T pooling configuration with existing video LLMs, demonstrating that it achieves state-of-the-art performance across long video understanding benchmarks while significantly improving computational efficiency through token compression. We also highlight the advantages of the Mamba module in enhancing performance and reducing inference time, particularly when processing longer video inputs, and show that temporal pooling outperforms spatial pooling in these scenarios. Section: Ablation of Mamba and Token Compression Modules. In this section, we present an ablation study that examines different token compression methods for models trained on a fixed input of 32 frames. Our standard storm model, without any compression, shows better performance across benchmarks compared to the baseline VLA, while keeping similar inference latency and the number of visual tokens. When we apply temporal sampling during testing, we can reduce the visual token count by half and lower the inference latency to about 58.7% of the uncompressed storm, all while maintaining performance. Using temporal average pooling during both training and testing further compresses the token count to 25% and reduces latency to 42.7%. This approach works particularly well for MV bench and MLVU, although it slightly affects long video bench and video MME. Similarly, spatial average pooling offers efficiency improvements, especially for long video bench, but comes with trade-offs for other benchmarks. We also implement temporal token sampling combined with either temporal or spatial pooling to enhance efficiency during testing. For example, the combination of storm with temporal pooling and sampling reduces visual tokens to just 12.5% and latency to 35.4% of the original storm, while still achieving similar accuracy to storm with only temporal pooling. The combination of spatial pooling and temporal sampling even yields the best performance on long video bench with significant token reduction. By merging temporal and spatial average pooling with or without test time temporal token sampling, we achieve even greater compression. Notably, our variant that combines all these methods, which has the highest compression ratio, uses only 3.13% of visual tokens and 29.5% of the original latency, yet still delivers competitive results. Compared to the baseline VLA, it achieves full performance on video MME, nearly full on long video bench, and high scores on MLVU and MV bench, making it appealing for efficiency-focused applications. We observe that while the uncompressed storm and its sampling variant perform best with the same 32 frames input, their high computational demands limit their scalability for longer sequences. In contrast, our storm with temporal pooling can extend the temporal context to 128 frames, improving performance without needing extra computation from the large language model, LLM. We analyze model efficiency in detail. Our findings show that as the sequence length increases, the latency gap between storm with and without token compression widens significantly due to the LLM's quadratic computation. For processing 256 frames, about 80% of the total latency comes from the LLM when no token compression is used. However, with a token compression ratio of 4, the LLM's latency drops to around 35% of its original value, indicating a major efficiency boost. The temporal projector allows for this token compression without sacrificing performance, and in some cases, it even enhances model performance while lowering computation costs. We also explore the effects of temporal sampling on the video MME benchmark, comparing the VLA baseline, storm without compression, and storm with temporal sampling using up to 128 frames and a compression ratio of 2. Our results show that the VLA baseline improves performance up to 32 frames but declines afterward. In contrast, storm maintains good performance up to 64 frames, and with temporal sampling, it continues to improve up to 128 frames while achieving a 50% token compression ratio. We believe this is due to the limitations of pre-trained LLMs, which, despite having large context lengths, effectively operate with a smaller context in practice. The combination of the temporal projector and sampling keeps the number of tokens within the LLM's effective context length while ensuring that the visual tokens retain rich temporal information. Lastly, we note that the Mamba projector adds minimal training overhead, increasing latency by only a small amount during full training. More importantly, since the Mamba module facilitates effective token compression, it leads to significant speedups in training and inference, as well as performance gains, ultimately reducing training costs. Section Summary. In this section, we present an ablation study demonstrating that our storm model, enhanced with various token compression strategies, significantly improves efficiency and performance across benchmarks while reducing inference latency. Notably, our best configuration achieves a remarkable compression ratio, maintaining competitive accuracy and enabling the model to handle longer sequences effectively without additional computational costs. Section: Our token compression retains visual information. In this section, we demonstrate that our token compression method effectively retains important visual information while significantly lowering computational demands. As shown in our qualitative results, even with a compression ratio of 47:1, our model successfully extracts relevant information for various video understanding tasks. For instance, questions such as, "Who wrote the poem in the video?" "How many times do news segments appear?" and "What is special about the last performance?" require detailed visual insights that our model provides. Our detailed analysis on the video MME dataset indicates that our approach consistently outperforms baseline models across nearly all task categories. Even in tasks that heavily rely on optical character recognition, our compressed model performs similarly to uncompressed versions while using only 25% of the visual tokens. This shows that our Mamba-based temporal encoder effectively compresses tokens by encoding spatiotemporal relationships directly into them, allowing us to maintain a high-level understanding with fewer tokens. Additionally, we highlight that our core design, which combines the temporal module with token compression, is adaptable to various video language model architectures. Our experiments with different models, vision encoders, and sizes reveal consistent improvements in both performance and speed, demonstrating the versatility of our approach.